So it's a real pleasure for me to be introducing my good friend and colleague, Dr. Yong Du. We got to know each other during our time together when I was at Hopkins, and he's a true gentleman and a world-class expert in SPECT imaging, and at the Department of Radiology at Johns Hopkins University. And he's going to be talking to us about SPECT imaging and its important role in alpha radiopharmaceutical therapies. Thank you, Yong.
Thank you, Armin. First, I would like to thank Armin for inviting me to give this talk. It's really my pleasure, and to show you what we do with SPECT imaging, especially for the alpha radiopharmaceutical therapy. Okay. Well, first, it's a disclosure, and some of the reconstruction algorithm we discussed today has been licensed to a company, and so I may get some royalty, and it's being managed by Hopkins. First, talking about radiopharmaceutical therapy, if you look at these figures, this show you the 5-year survival rate of different cancer types, and the blue line shows the localized tumors, and the orange or the yellow line bar showing the metastatic cancers. You can see compared to localized single tumors, solid tumors, the metastatic tumors has very low survival rate, and for different type, and because the solid tumor can be operated by removing the tumors, but for metastatic tumors, there is less treatment options. Either use chemotherapy, or you can use nowadays can use the immunotherapy. But both chemotherapy very damage the patients, and immunotherapy usually can be very effective in the early stage, but the patient usually develops like resistance very soon. So also in recent years, people have found now radiopharmaceutical therapy very reliable radiopharmaceutical targeting specific tumor target can be labeled with radionuclide emitting alpha or beta emitters and can very effectively kill cancer cells, and they are very viable treatment options for patients that chemo refractory or it's not eligible for radiotherapy or operations. And so there's a great increase of interest in using radiopharmaceutical therapy to treat cancers. And if you see this figure on the bottom right, there's an exponential increase of interest in developing the alpha-emitter therapy during the last couple of years, and the exponential explosion for that effort. And the reason for that, there's 3 major factors happening in the last few years. And first, there's a lot of available alpha particle emitter nuclide on the market, so we can do the labeling, for example, with actinium, lead-212, and radium, and thorium, even astatine. And also now there's because research on the cancer, there's a lot targeting molecules that can be used to target specific cancers and specific target on the different cancer type. Also now recent years there's more development in the chelator that can be used to attach this heavy radionuclide to the target molecules. So that can improve the target stability, and so we can have a useful radiopharmaceuticals to treat patients. So all those factors have contributed to the increased interest in the radiopharmaceutical therapy for cancers. So basically now there's 2 types of radiopharmaceutical therapy. One is labeled with beta emitters, basically electron. Those include like, for example, the IDA-131, the lutetium-177 labeled dotate, is treated for neuroendocrine tumors, and the lutetium labeled PSMA is treated for prostate cancer, and yttrium-90 is a pure beta emitters. It's usually labeled on the microspheres, treat liver cancer. And because beta particle is basically electrons, so it's very light, so it has very low energy transfer. Therefore, we usually need like thousands of electrons to kill a single cells. And because that, the damage can be is repairable. On the other hand, alpha particle therapy is also a very effective treatment. Example include actinium labeled PSMA, it's very popular, and radium labeled chloride, and so basically the market name is Delphigo, and also some labeled HER2 to treat breast cancers. Alpha emitter basically in the nuclei of helium, so it's very heavy. And so it has high linear energy transfer. Usually, like because that, then it's only need like 2 or 3 of our particles to kill a cell. Now the mechanism basically it causes repairable DNA damage. Because of that, there's a very less resistant development, and it's very potential kill cancers. As we can see for the figure to the right, beta particles has longer range, but because low energy transfer. It's need a lot of beta particles to kill a single cancer cell. But alpha particle, on the other hand, very short range, only like 3 to 8 microns, but it has very high energy, high mass, so it has a high linear energy transfer, so it can kill the cell with just one single or two alpha particles. So it's very effective. This can be demonstrated in this very famous figure published in 2016. Actually, now using alpha-emitter to treat cancer has been a long time. Now, if you remember, Madame Curie, she's like used radium to treat cancers many, many years ago. And actually, now like other scientists like Dr. Girls in Hopkins, he's did his PhD on alpha therapy like 30, 40 years ago. So it's continued research effort. But because chemical and availability of radionuclide, it's not really flying, but as I just said, there are some contributing factors in the last few years to the great increase interest in use alpha radiopharmaceutical therapies. One example is this one figure shown here. It's done in Germany, and they basically now this patient is a field lutetium therapy, basically beta therapy. So they treat with actinium-225 labeled PSMA. You can see now before treatment, the patient has a lot of tumors in the body. It's basically spread to everywhere. But after 3 cycle of the actinium PSMA treatment, the tumor basically gone from the bodies, and the PSA is also reduced from 2,900 to like 0.26. And after another round of the consolidation therapy, you can see no tumors. Also, the PSA has greatly reduced. I think this figure tells everything how effective actinium alpha therapy is. And this actually it's kind of like starting point for the increased interest in alpha therapy during the last 10 years. So, and in order to treat patients more effectively, we need to calculate the dose. However, the current treatment usually give a patient a fixed dose. For example, lutetium therapy, dot people only give like 200 microcurries fixed dose, and they don't changing this based on the patient specifically. However, this may cause an optimal dose, either underdose or overdose the patient. And in order to have better treatment efficacy, we want to do the treatment planning to determine how much activities we want to inject to the patients. The reason for that, there's a research done in Europe, like in 2021, they have a large scale clinical trial, phase 2 clinical trial, use yttrium labeled microspheres to treat liver cancer. However, that clinical trial failed. The reason failed, they studied the retrospective studies, compare patients receive fixed dose and personalized dose. So they concluded in that, basically, that trial failed because they did not do the personalized radiation dose. And they further did a dose analysis. I can see compare patient receive the personalized dosimetry and use a standard dose regime. And we can see there's a very big difference in the survival of patients. So the patients receive personalized dosimetry has like 20.6 months of average survival. But for the patient receive standard dose, it's only like 10 months survival. So there's a very big difference. In addition, they further look at the dose to the tumors. They compare separate tumors receive like 200 gray compared to those receive less than 205 gray. And you can see now for tumor receive large dose above 205, there's great survival rate, and the average surviving like 26 months, and compared to like only 7 months for patients receive a dose less than 205 gray. So now this data clearly demonstrates the necessary to optimize the dose for patients to the personalized dose, also to look at the effect dose to the tumors. So that's a rationale to do that. So now the goal of us to do the patient-specific treatment planning is to avoid the significant toxicity to the normal tissues, but also want to maximize the therapy dose to tumors, as I showed previously, 205 grays kind of threshold. We want to treat patients for this specific radiopharmaceuticals. And now we also want to do it patient-specific because each patient has different anatomies and has different biodistributions and uptake and the biokinetics. So we need to do this on the patient level and individually, which for each patient. So ideally, now you want to have a really good therapy efficacy. You want to do the treatment planning. Basically, we will administer the planning agent, usually a surrogate agent, or the low dose of the therapeutic agent. Then we can measure the distribution of those radiopharmaceuticals in the patient body as a function of time. Then based on that, we can calculate organ and tumor dose. And based on that, we know the target tumor dose or those limited organs total tolerant dose, we can calculate the therapeutic activities, how much we want to give to patients. Then we use that, we can guide the therapy, how much we really inject into the patient to treat the cancers. And we can do this through multiple cycles. After give them treat the therapeutic dose, we can do the imaging or measurement again, calculate new dose for next cycles. We can repeat this several times till the cancer is totally removed from patients. However, to do that, we need to know the distribution of the activity in the bodies. And this is showing basically how we calculate the radiation dose in the patients. Basically, the absorbed dose is defined as the energy absorbed per unit mass. That's how much energy deposited in the patients. Basically, in our formula is like number of disintegration, so number of decays multiplies the energy released from each decay and how much energy deposited. This cartoon here show you now, for example, in the patients, if we have taken the lung, heart, and kidney, and intestine and liver. So all those radiation, when they decay, they will emit different particles and energies. They can being deposited locally, and they can also transfer to the propagating to neighbor organs and deposit in the neighbor organs. The example here is showing all the energy transfer from other organs into the liver and energy deposited in the liver itself. So if you add this together, as shown here, this gives us a total energy deposited in the liver, which divided by the mass of the liver will give us the total absorbed dose in the liver. So that's how we calculate dose, and this defined as the energy here now absorbed per unit mass, and this basic unit is gray and define 1 joule per kilogram. So we can see there's very complete calculations, but luckily energy released per disintegration per decay is a kind of constant for each radionuclide, and also the fraction of those. Ideally, we want to calculate based on the patient levels, but in the merged scheme, we really simplify use the standard phantom. All those factors here, circled in the green circle, will substitute with a single factor called S factors, the contribution from each source organ, for example, lung to a target organ, here it's liver. So when we have this, we can add all the value together based in the merged scheme. We can have the total activity accumulated in each organs and the source organs and this S factor from the source organ to a target organ. For example, liver in previous slice, then we add them together, will give us total deposit dose in the livers. So we can see since S factor is calculated based on the standard phantom, so it's pretty much fixed. And all we need to now to calculate patient dose is to calculate the accumulated activity. To do that, we need to know how the activity changing as a function of time in the patients. And this, because therapeutic radionuclide usually have a half-life of days. And so we need to measure this activity in the body in the patients up to days, even weeks. And when we get this time activity curve of activity distributions, then we can integrate as a function of time to infinity. This gives us another concept called time integrated activity, which can be used in this equation to calculate total dose for each organ. So that's how we do those. So the key factor here, we need to know the accurately measure activity distributions as a function of time. Then we can do these integrations. Now, because it's in the patient bodies, we cannot use you try samples to measure activity. So to do that, we have to use an imaging method. We can either use SPECT or use the PET. However, because in PET, you really have to use the F18 carbon 11 gallium to do the imaging, and those now that usually not therapeutic radionuclide, they are surrogate radionuclide, and because they usually have a short half-life, we can only do a snapshot, and like 1 hour or maybe 3 hours post-injection, we can now do the measurement several days after injection. So for radiopharmaceutical therapy, dosimetry SPECT is mostly commonly used because most therapeutic radionuclide also emit gamma rays or X-rays can be direct imaging by SPECT. Then we can monitor the distributions as a function of time over a long period, and we can do this on specific patients to measure distribution specifically. So SPECT is ideally for doing radiopharmaceutical therapy dosimetry. However, this figure shows you how we can use SPECT to do the activity estimations. Basically, now we can measure SPECT imaging of the patients, like 0 hour post-injection and 4 hour, 24 hours, 3 days, and 6 days post-injection. From that, we can do the SPECT acquisition. Then we can reconstruct the image and draw the regional VOI of each organ in the CT image. Then we can measure organ activity, for example, liver here, based on the series of SPECT imaging, give us a liver activity as function. And showing here, we can have a snapshot at different time point. And we got this function as a time. Then we can do the curve fitting to get the time of the curve, which we can do the integrations to calculate the total time integrated activity in each organs. Then we can do the dosimetry calculation. However, SPECT has its some weakness compared to PET. In PET, we have the coincidence detections. We don't need a collimator, so PET has a very high sensitivity, usually like 1% kind of sensitivity, and it's also very high spatial resolution, is the 4 or 5 millimeters as country. Because SPECT uses collimators, so it's have very poor sensitivity. It's like 2 orders less than compared to PET imaging. Also, it has a poor spatial resolution, really 1 to 2 centimeters or even worse. So now there's some inherent factors affecting image quality, as shown here. So now we have the attenuation. For example, now we have ideal cells, and ideally we can detect the single dirt function, showing the strength of the cells. But because attenuations, then the activity in the different depths of the bodies can be detected differently. Now, the one deeper in the body will have a short detection, it's not small detect intensity, and the one close to the body surface will have a higher signals. So that's attenuation effect. Also, the photon can scatter in the bodies through multiple scatters, and because common scatter change directions and energy, so they can still be detected. And if energy changing small, they still can be detected in the energy window and being recorded and affecting image quality. And also, because photon can penetrate the hole is have a limited size, and the photon can penetrate the septal of the collimator, or scattered in the septal, or causing light X-rays, and they can be detected in the energy window and causing blur of the image. So that's what we call collimator detect response functions. Basically, resolution blur, and also resolution blur can introduce partial effect for small object. In addition, because lower sensitivity in SPECT, so the noise is really high. And in case of alpha-emitters, there's multiple peak emission, and the crosstalk and downscatter between different energy peaks can also contribute to the degrading the image quality. So there's many factors in SPECT can affect image quality, and this figure showing how those different factors can affect image in the cardiac imaging sense. So there's images on the left showing the active patients, and in the myocardium, and this showing the attention map. And this is when we don't have any physical factors here, this image shows in almost identical to the original activations. It's ideal situation, but now when we add attenuations, the image in the center has more attenuation coming to the peripheral. So we have dark in the center and the bright on the edge. And when introducing resolution blurs, image become blurred. And when we add scatter usually like a low frequency background information can reduce the contrast and also introduce some additional blur or artifact in the image. And then we have noise, can see image becomes very hard to read. And we can reduce them some with low pass filters, but image quality is much worse compared to the original image. Luckily, during the past several decades, people have been heavily researched how to develop reconstruction algorithm and how to compensate for those degrading factors. And once we found that, if we model those physics degrading factors during the iterative reconstruction process, we can gradually remove those factors and improve image quality and quantitative accuracy. For example, this figure shows you a typical step of the iterative reconstruction. Now we have the imaging space and projection space, and from the initial estimation, we can do a forward projections and compare with measure date, and which give us error term, which can back project into the imaging space, and we can use to update the images. So then people found if we model physics during this forward projection and the backward projections process, we can gradually remove the attenuations or resolution blurs or those kind of factor and improve image qualities. One typical algorithm for that is the LEM algorithm, and we can model the factors in the projection matrix, or we can model them on the fly or calculate it beforehand into the matrix. So that we can solve this problem. And this example shows how the effective the image reconstruction-based compensation method can remove those degrading factors. Again, now we have this phantom images, and we have from previously, we have the feedback projection reconstruction without any compensation, but without the degrading factors. And we can see if we include attenuation compensations, image becomes more uniform, and we don't have the dark in the center and the bright on the edge. So image more uniform. And when we include the collimated detect response, basically resolution recovery, you can see it's the edge of the myocardium becomes much sharper. And if we do the scatter corrections, it's hard to tell from this image, but if we draw the profile, we can see this image is more close to the true activations as compared to the original phantom. So basically now this shows we can improve image quality and quantity accuracy with the physics modeling doing iterative reconstructions. So that's how we do the quantity reconstruction. However, when we apply those to alpha emitters, there's some additional challenge that's not commonly seen now when we do the spec imaging of technetium or indium, because now there's the alpha emitters. First, now it usually have very complicated decay scheme with multiple daughters. Some of the daughters may have a long half-life, and because now once the decay become different element, they can detach from the original radiopharmaceuticals and become a free ion in the body, and those ions can redistribution and causing like accumulating in the kidney, causing additional damage. And so we need to know the distribution not only the parent radionuclide, but also we want to know the distribution of daughter radionuclide to calculate the dosimetry and the toxicity. Also, because decays are very complicated, usually there is the multiple gamma rays and X-rays. They are usually now emitted in a low abundance. And so we need to imaging all of them. Also, we need to correct the scatter crosstalk between those peaks. Also, I will show later, there are also a lot of high-energy photons emitted from those alpha emitter decays, and those high-energy photons can penetrate through the collimator septals and being detected in the detector, causing downscatter contamination. There are big effect also on the image quality, as we can show later. Additionally, because the alpha emitter is highly potent, so we really inject very small dose, usually like 200 microcurries or even less, compared to like technetium, we can inject 20, 30 millicurie. So it's very low activity. So the image is very high noise, low count. So those are very significant challenge for improving image quality for SPECT imaging of alpha emitters. This example show you actinium and the labeled antibody, and there's chelator of the actinium connected chelator to the antibody. However, when actinium decays, alpha particle is very heavy. So as you remember, it's a basic nuclei of helium. So there's a big momentum, and due to the conservative of momentum, the actinium, the decay, the fission, also will have quite large momentum, and this can cause it to break from the chelator and become free ions, and it's further decay into other daughters, such as bismuth. And those free ions can get into the blood and being circulated in the blood circulations. Most time they accumulate in the kidney and causing damage to the kidney. So one major thing for actinium dosimetry is we want to know how much bismuth accumulate in the kidney, and we want to calculate dose for that. So that's reason for the challenge for the SPECT imaging of 5 emitters. And again, now this show you the full decay scheme of actinium-225. We can see there's multiple daughters, and there's two peaks, and the one 280 keV and 440 keV. The 218 keV from fission and the immediate daughter of actinium, and there's another the 440 keV is from the bismuth, which has a 45 minutes half-life. And we can see because the half-life is short, so the fission distribution usually very close mimic the distribution of actinium. But due to the circulation and the free ion accumulating in the kidney, the bismuth distribution usually is different from the fission and actinium. So in the spectrum, we can clearly see the peaks of 440 keV and the 218 keV of fissions. And there's a lot of peak around 80 keVs, and we can see around here. Those are kind of from multiple isotopes. Also, 80 keV is the kind of like character X-ray of lead, which is a common material for the collimators. So when those hydrogen photons interact with the collimator light, then they can cause the light to emit characteristic X-rays and can significantly contaminate the count in this peak. So even though this peak looks very sharp and high, look very attractive, but we cannot really imaging this because there's a lot of light X-rays, also multiple peaks combined together. So it's hard to tell which is from which. So we usually don't imaging this. So instead for actinium, we only imaging the 218 as fission as a surrogate for the actinium distributions, and for 40 keV to measure the bismuth distributions. Now this is another example of radium-223. Again, we can see very complex decay scheme, and there is several peaks we can used for imaging. And again, now we can see 80 keV peak, but that's overlapping with light X-rays, which is not very useful. One thing I forgot to mention here, this blue lines is the on the south. We can see now the peaks are very clearly identified. However, when they put the activity in the sphere in the water cylinders, we can see due to scatters, those peaks are quite overwhelming by the scattered photons. And there's like the activity here, that's contribution from the high energy photon downscatter. And we can see there's a significant scatters and downscatter contaminations, and images is going to be really low pool qualities. Similar here, and we can see now without scatter, the peak are really easily identifiable, but with scatter and downscatter, the peak is very basically overwhelming by the scattered photons. Similar case with thorium. Thorium can decay into radium, so we have other problem showing in the previous slides, and the additional contribution from thorium. This showing the photo peaks that can be imaged with abundance less than 2%. And first we can see they are very small, like a 10 of 25%. And some those 80 kVs usually can be overwhelmed by the light X-rays, and we can only image like 200 kVs. However, they are very close to each other, so there's going to be a lot of crosstalk when we're trying to image thorium and radium at the same time. Similar case with the light 212. Light 212 is not alpha emitters, it's actually beta emitter, and daughter is actually alpha emitter. So now, again, because the redistribution of the daughters, so there can be a problem for light 212. And people have using light 203 as a surrogate for light 212. It can now ideally indicate the distribution of light 212, but it cannot be used for indication of where the daughter goes. So that's one disadvantage of the light 203. Again, there's a peak showing now what we can image, and there's 70 keVs, close to 80 keV, can be OM by the light X-rays, and also there's a 230 keV, that's very good abundant, but there's very high energy, about 30%, that can downgrade image qualities. So now, with all those issues, how are we going to solve this? How are we going to get images with the alpha emitters? Now, first, we can optimize the imaging protocols. Now we can optimize the acquisition. I mean, we want to increase time so we can get higher count to reduce noise. We also want to design the energy window carefully to narrow down the scattered photons to try to record as much peak photon as possible. We can also use the adaptive acquisition protocols, using different time of different views to acquire as much information as possible. Last thing now we can do, which I focus on, is to develop reconstruction algorithm to compensate all the imaging physics and also other particular factors can affect alpha emitters. And we can also develop a simultaneous reconstruction algorithm to recount multiple peaks, multiple radionuclide distribution at the same time. And the other thing now, because what we get is what we see, and what we see is what we get. So we are linked by the hardware. So the best solution is to design next generation SPECT system, in which we can use a new detector such as a semiconductor detector to provide high energy resolutions, so we can separate all the peaks from each other, and we can also use new collimators to increase sensitivity and spatial resolutions. So next I'm going to show you some examples of the reconstruction algorithm and the new camera that we're working on. First, the quantitative SPECT reconstruction. So what we do is we develop those model-based reconstruction with the cross compensations. Basically now from, for example, the radium and thorium cases. And in the thorium radium imaging, we have two isotopes, one is thorium, one radium. First, now we can record projection in the radium window. We can reconstruct them with a compensation for the attenuation, resolution, and scatter, which give us the radium attributions. We can similarly reconstruct thorium projection date with correction for the attenuation, resolution, and scatter, which give us thorium activity. However, because now they are acquired at the same time, there's crosstalk contamination between those two radionuclide, and for that, we need to compensate for the crosstalk contamination. To do that, we can now, based on the radium activation distribution, we can do the projection by model the attenuation and the detect response and the scatter into the thorium windows. Similarly, we can, from thorium image distributions, we can estimate the projection into the crosstalk into the radium window. So by doing this, we can estimate the crosstalk. Then during the next round of reconstruction, we can add those estimated crosstalk into forward projection data and do the compensation, which give us now crosstalk compensated images. Because of the first round reconstruction, this includes crosstalk, so this will be overestimated. So we can do this iteratively over multiple iterations, can gradually improve image quality, and we can do the final reconstruction with crosstalk removed, also compensate for the attenuation detected and the self-scatter, which give us much improved radium and the thorium images. And this slide shows you the details, how we model all the scatters and the contribution, because those thorium or radium can emit multiple peaks. We have to model each individual peak separately. Also, the scatter spectrum is very complicated. We usually split the scatter spectrum into a different energy range from like 100 up to 500 keV, and we can model those different scatter energy ranges individually and add all the contribution together. It will give us a total estimate projection in the thorium window or radium windows. So we do this for both thorium and radium. You can see it's very complicated step. And however, we have integrated this into a single reconstruction algorithm. We can model all those contributions and taking the projection data in multiple energy windows. For this case, we can take like 200, I think that's radium window, and 269 is the thorium window, and also additional 154 keV energy windows. We can, or even more energy window can be included in here, and we can do the reconstruction to produce the thorium images and radium images at the same time. Also include the correction for all the imaging degrading factors. So to validate this, we did the phantom study, and there's two NEC standard phantom. We have 6 spheres. We filled them with pure radium and pure thorium. And we can see here the blue spheres are filled with radium, and the clear spheres filled with thorium. Then we fill the phantom with water as a background for scatter, and the imaging on the Siemens Symbia SPECT CT system with the median energy colorimeter. Those are accreditation protocols showing the energy windows and the number of projections. And we did one thing is a 10-second preview. So this gave us like around 10 minutes accreditation time. So it's very short time for SPECT. And this show you the image on the day one after we just fill the phantom, because we have a pure thorium radium. If you remember, thorium decay into radium, but on the day one we have a pure thorium and a pure radium. We can see the spheres filled with the thorium activity only show up in the thorium image, and this one here, and the spheres filled with radium activity showing up only in the radium image. However, on day 14, because thorium will decay in the radium, so in those thorium spheres, we also have a certain amount of radium showing up, and we can clearly see those spheres showing up in the radium image. On the contrary, the radium decay doesn't show up in the thorium image because it's daughter of thorium. So this clearly shows now that we can separate the two radionuclide in the reconstruction. And one thing you need to note is that this very short accretion, it's only 10 seconds, means a 10 minutes accretion. So in this way now, if you want to do imaging patients, whole body, we need 3 bed positions, and 10-second accretion convert to like 10 minutes accretion per bed position. So we can imaging a whole patient within about 30 minutes. So that's very good for doing the patient, because a lot of patients with cancers, they suffer from like a lot of pain and they cannot stay in the bed for a long time for imaging. So we want to reduce imaging time and finish accretion as soon as possible. At least those figures demonstrate we can do that. And this show you now the radium whole body imaging, and this actually simulated from the Siemens simulation based on patient data, showing the image at 6 days after injections. And we can see for radium, most uptake in the bone, and unlike a lot of radionuclide, which was extracted from bodies through the urine, radium actually accumulated in the GI tract and eject from the colon. So we can see there's a lot high activity in the colon showing here. That's very interesting. So similarly, we also did validation with the actinium phantom, again with the sphere and with white background here. And here showing the accretion protocols. I'm not going into the details, but we do imaging in the 2 energy windows. One is the Frisian 218 keV energy window, and this one's 440 keV windows. And this reconstruct image showing the activity in the Frisian window and BISM windows. And the estimated quantification errors in the Frisian window is about 8%, and in the bismuth is about 1%. Again, we're also looking at precision of activity diffusion estimations, and this we let the activity decay, and we measure the quantify the image and calculate the variance in the estimated activity. You can see when they up to like even though 0.12 microbarcule, we still get very good variance in the image. So the method is accurate and precise. And we also did the fun animal studies. The figure here showing a rabbit, normal rabbit. We injected the actin labeled this dimmer and through the catheter directly into the liver. You can see the accumulation of in the 218 windows in the liver very interesting. Even at 1 hour, so we can see the difference between the distribution difference between the actinium and the bismuth. Bismuth we can see a lot in the kidney, but very less in the liver because it's dissociated from this compound and going to blood and accumulate in the kidneys. Again, this is the rabbit now has a tumor model with a tumor in the liver, and we can see there's a accumulation of kidney in the liver at 24 and 72 3 days and 6 days post-injection. You can clearly see the tumor accumulation. And also, if you look carefully, you can see the difference in the kidney uptake between the base window and Friedman windows. So we are now working on trying to quantify those data, and hopefully we can do the dosimetry calculations. On the left is the reconstruction with our method with full compensations, and on the right is the reconstruction on the software and with attenuation correction only. You can see with our correction compensation reconstruction, we removed most of the scatters, and we can see the liver, the tumor is much clearly identifiable with very high contrast as compared to the GE reconstruction. Again, where there's a Friedman window, bismuth window, the one on the top is about 8 hours post-injection. The one on the bottom is about 29 hours post-injections. So based on that, now we can quantify the uptake in the kidney, the tumor, and all the other organs. We're also working closely with Dr. Lin Jianmeng from UIUC to develop a new SPECT system, especially for alpha-emitters, which we call alpha-SPECT. So traditionally, the SPECT imaging detection of gamma photons using scintillation detectors shown on the top here. So basically gamma photon goes into the crystal and deposit energy, become visible photons, and those visible photons can spread into the crystal, and some of them, usually 20%, being detected by the PMT, photomultiplier tubes, behind that and being amplified, detect the signal. So there are two stages. First, generated scintillation photons, then being detected into the PMTs. So this not direct it's called indirect detection. So efficiency is very low. Also now for each photons, it's usually take about 30 to 40 EV to generate. On the other hand, there's a semiconductor detectors. When the gamma photon goes in, it will break down an element into a hole and electron pairs, which under the influence of electron field will move into the cathode or anode, being detected directly as the electron signal. So this is a direct detectors. And so now compared to this, it should be high efficiency. Also for those electron hole pairs, it's only like a few keV to generate them. So now we can have much more hole and electron pairs compared to the number of photons here. So in summary, so in total, the semiconductor will have much higher efficiency, and so it will produce higher energy resolution in this way. So this figure shows example of semiconductor detector SPECT system compared to the clinical SPECT system. And this showing the actinium and the different X-ray and gamma peaks we can detect, and showing here along decay chain. And the figure here on the left is showing a sphere, 6 centimeter spheres filled with actinium. And the red line is a detected spectrum from a CD detector, and the blue line is from conventional scintillation detector. You can see there's much narrower peak showing good energy resolution compared to the traditional SPECT system. The image to the right is showing we put spheres into a 20 centimeter diameter cylinder. That means a lot of scattered photons. Again, the peak of each isotope can still clearly seen in the CD detector in the right spectrum here, but in the blue spectrum, that's matter from the Symbia, scintillation detectors, and you can see the peaks are much blurred, and there's a lot of scattered photon contributions, cannot be separate. So this clearly shows the advantage of using CD detectors to detect each peaks of the alpha emitters. Again, based on that, we can also let's show you the individual detect modules, and we can couple each individual detectors with a pinhole or multiple pinholes. And based on that, Dr. Meng developed this compound eye cognitive design ideas. Basically, from the inside has the compound eyes, each has many hundred of individual eyes can look at the image, and you can combine them, generate really good images. So the idea here is similar. We can have each individual element coupled with the individual collimators, which gave us individual eye element here, and we combine them together, 100 of them. We can have multiple common eye design, and this show you the actual direction, and this show you the cross-section view, and we can see the multiple detectors. In this way, we can improve both sensitivity also maintain the resolution because pinhole collimators. So with that, this show you they build this what we call alpha-spec mini system for small animal imaging. It's basically have 6 panels of detectors, and this individual detector, the 2 by 2 centimeters, well, 4 detector landed together, and have the pinhole, the multiple compound eye collimator design. And it's showing you some example images. Now we have actin decay, and again, instead of only imaging the 18 kV of friction and the 440 kV bismuth, we can now imaging the 100 kV of actinium, and also some other peaks like 117 kV peak of thallium. So now we can have the individual images for each individual nucleide. So that is the unachievable on a conventional SPECT system. And this figure shows the tumor uptake and the kidney uptake. We can see clearly there's the less bismuth in the kidney, but there's more bismuth. Sorry, there's less actinium in the kidney, but there's a lot of bismuth accumulation in the kidney. So clear indication of the bismuth detached from the antibody and accumulates through the blood circulation, accumulating in the kidney. So that's why it's important to imaging them separately and for dosimetry calculations. Again, this shows liver uptake. And for this imaging, we only have 1.5 microcurie injections. Imaging time is still a little bit long, it's 2 hours. Again, this shows you the tumor uptake in different windows at different time. Now we can see even after 6 days, the uptake in the tumor. So the previous design of SPECT Mini is the small detector. So the field of view is really small, like I think it's 2 centimeter around that range, field of views. So in the SPECT Mini 2, so the second generation, we use more detectors and large panels. So we increased the total field of view to 6 centimeter actual direction, 8 centimeter actual direction, and 6 centimeter transactional direction. So now we can now image the whole body of a mass. Now again, we can see the distributions of different isotopes with different imaging. This show you a bone scans, basically in a pure actin inject in the body. And we can see now different windows showing here. So we also can do dynamic imaging because this detector is a fixed stationary detector and with a full 3D coverage. And now we can have a injection, starting from injection, we can do a dynamic imaging on here, showing the image required at the 5 minutes post injection image at 1 minute. I'm not sure what's that mean though. Okay, so sorry, this is 1 minute post injection, but imaging occasion time is 5 minutes. And here now the imaging requires different time, like 1, 2, 3, up to 1 hour. So we can see the changing of that activity in the bodies. So that's really very useful for imaging not only alpha emitters but also for beta emitters. Uh, Again, let's show you the radium image, we just acquired I think 2 weeks ago, and because as we showed earlier, the radium mostly accumulating in the bone. We can see here clearly the tumor uptake in the bones. So for this studies, we use a high sensitivity collimator, so the resolution really improved. We do have a set of a high resolution collimator, and that's what we're gonna do next time. So when we do imaging, we want to acquire better imaging as compared to this. So again, now let's show you the ability of the using CT tech to debug different system. So so with this, now we also have 2 alpha-spec systems under development. One is a human system supported by a U1 grant. One is a large animal system supported by the R1 system, R1 grant. And so the design target for the both system, we want to have a 0.1% sensitivity. It's about 100 times higher than the current clinical system. We target an energy resolution about 1.5 to 2% at 140 kV. And as comparison, clinical system right now has 10% energy resolution. And the target spectral resolution is only 5 millimeters. So now compared to the current PET system, as compared to the current clinical system is 1 or 2 centimeters. So mm, so this show you the basic design key features. Now we use CT detectors and also the compound eye design with multiple pinholes, and we can have different pinhole for high sensitivity or high resolutions. Uh, so this shows you the detect element we use and also electronics showing here. And no, there's like a 2 by 8 detector. So we have a 2 by 20 centimeter detect size to build the full range detector. Simulated the images based on the configuration, showing a rabbit and this kidney. And this is what we acquired from the Siemens system using a rabbit. We can see now, we already showed the slides earlier. We can see the kidney, but it's just blob. We cannot see actually detailed structures. But in the SPECT system, because we have a higher resolution, we can see the cortex of the kidney and the different structure in the kidney. So it's showing the better resolution. Also, if you look compare here, this use 100 microcuries and 60 minutes, but this only use like 1/7 of activity with like 1/4 of the location time. We still get really good image quality compared to a clinical system. So hopefully, once we get this system, we can do more validation with animals and human studies and can use to get, future therapy clinical trials here in Hopkins. Again, now we recently also get another grant to build a small animal system, which we call F-scope. Basically, the two figures are showing here. Now the top line is the activity distribution in the kidney. The bottom line showing the bismuth distribution in the kidney. You can see now, even though now we want to look at whole kidney, but the distributions inside each organ, now subdivision of organs are different. So now because alpha-emitters only have like 50 to 80 micron range, so we really want to look at the diffusion of activity at micro range. So we do the calculation in the microdose, and so this gives us better idea of toxicity and the therapeutic efficacy. Again, on the left, you can see the activations in the tumor, and then now see it's also non-uniform. So for the F-scope, we try to develop much higher resolution small SPECT system, which we're targeting resolution about 100 micrometers. So for this, hopefully we can imaging the organs or tumors with much better resolution and to provide ideas. Now have alpha particles kill the cancer and damage the normal organs for microdosimetry calculations, also for efficacy studies. So that's the next thing we will work on. And so a lot of interesting happening. So in conclusion, now interdosimetry very important for radiological therapy, especially for our therapies. And imaging alpha-emitter is very challenging, but it's doable if we have a good quantity reconstructions. So for clinical system, we can have accuracy to less than 10%. And this can be, we can also provide certain information about distribution of daughters, such as actin and bismuth. And but now if we use the CT-based cameras, we can have a much higher energy resolution. Then we can separate more daughters and combine with normal combinator and same design. We can do the imaging of not only alpha-emitters, but all the daughters. So with that, I think that's the last slide. Thank you. Yeah, no, this is all the fundings and the people I'm working with. Thank you.